Okay. So we're going to have Dawn Song to tell us about decentralized data science made easy, and a few quick words about Dawn. So she's a professor at UC Berkeley, and she also did her PhD there. So her work has received multiple awards. So she's the recipient of the MacArthur Fellowship, Guggenheim Fellowship, NSF Career Award, the Alfred Sloan Research Fellowship, and many more. And her work also received a lot of best paper awards at top conferences. And she was also faculty at CMU before joining UC Berkeley. So Dawn, you can start whenever you're ready.
Great. Thanks a lot for having me. Yes, and right, sorry that I couldn't be there. My flight had mechanical issues. So, right. Okay, so let me get started. So today I'll talk about decentralized data science made easy. Right. Okay, I'm a professor at UC Berkeley and also the founder at Oasis Labs. Okay, great. As we all know, data is a key driver for modern economy and the lifeblood of AI and machine learning. And more data is being collected every day, and value from these personalized data now is a significant fraction of global GDP, and the global data economy is growing exponentially. However, a lot of this data is sensitive and unprecedented, and we are all facing unprecedented challenges in how sensitive data is being used. So for individuals have lost control over how their data is used. A lot of users' data is being sold or abused without users' awareness or consent. And a lot of the data is being sold under the premise that the data has been anonymized. However, volume of research has shown that anonymization is not sufficient to protect users' privacy, as illustrated by this a great case study done by New York Times, showing that from anonymized mobile phone location data sets collected, they were able to track the location of a Secret Service agent with former President Trump. And also for companies, companies continue to suffer from large-scale data breaches where attackers steal sensitive information of hundreds of millions of users or even billions of users in each of these incidents. And also, so CCP and GDPR, these are great first steps for privacy regulations, but however, they also have been very costly for businesses. And furthermore, even more important is that a lot of the valuable data is not being used. Right, so this valuable data sits in data silos and could not be used due to privacy concerns. And today we are facing all these huge challenges for how sensitive data is being utilized. And this issue will only continue to be more and more severe. And if the issue is not resolved, it could hinder societal progress and even undermine human values and fundamental rights. And hence, there's an urgent need for a new paradigm building a responsible data economy. And what do I mean by building a responsible data economy? Here are a few goals and principles of a responsible data economy. First, we need to establish and enforce data rights. These data rights are foundations of data economy and can prevent misuse and abuse of data. And also, we want to ensure fair distribution of value created from data. For example, users should be able to gain benefit from their data. And more importantly, we want to ensure efficient data use to maximize social welfare and economic efficiency. And in order to build a responsible data economy and achieve these goals, essentially we need to enable responsible data use and take a very different approach than the current approach. So in the current approach in Web 2.0, it's a centralized solution where users' data is actually being controlled by centralized trusted third party. And the computation over data is done in centralized fashion, even though they may be done in a distributed setting, but it's still controlled by centralized parties. So instead, we want to enable the data use without relying on centralized trusted third party. In particular here, this is the ethos of Web 3.0, where users maintain control of their data, and the data usage is done in a fully decentralized manner so that we do not need to rely on any centralized trusted third party. And this helps users maintain their data ownership and hence can encourage user participation. In order to achieve this goal, luckily, there has been huge advancements in responsible data use technologies in the research community. And in particular, thousands of papers have been written on related topics, including secure computing, such as MPC, FHE, federated learning, and other technologies. However, with these thousands of papers that have been written, if we actually look at in practice what actually have been really deployed, what actually have been used, it's a huge difference. Unfortunately, very little real-world usage and deployment of these advanced techniques for responsible data use are actually in practice and deployed in the real world. And why is this the case? Why are these thousands of papers mainly just sitting on the shelf? So one key challenge we identify here is, besides developing the original algorithms, the actual development and deployment of technologies for this responsible data use and for decentralized data science is actually too expensive today. So here I'm going to give you first a couple examples of our real world experience to at least illustrate the point. So the first example that I'll give is a recent launch that we did. So Oasis Labs actually is a technology provider for a recent huge launch in partnership with Meta, Instagram. So here, Meta, Instagram, together with Oasis Labs and also 3 university partners launched the first large-scale, first of its kind AI model fairness measurement. So, so here, what is the AI model fairness measurement first? So for example, with Meta and Instagram, they have hundreds of millions or billions of users, and they use various AI models to recommend, to do recommendations to users and to provide better services and so on. And the natural question is whether these AI models are actually fair, whether they have biases. So for example, whether these AI models will treat male, female, or non-binary people differently. And in terms of societal fairness and so on, this is a very important question. So the question is, how can we actually do this AI model fairness measurement? So in order to do this measurement, essentially, we need different pieces of information. So for example, Meta, the AI model provider, for a given user, it knows because it has the model, so it can get the, for example, the model inference results. However, Meta does not necessarily know the needed sensitive attribute of the user to be able to conduct this AI model fairness measurement. So for example, Meta doesn't know for a given user whether the user is male, female, or non-binary. So in this case, then what the solution that Meta came up with is to work with a survey operator. And then in this case, the survey operator could launch a survey, for example, for Instagram users, which is the case in the recent launch. And then users can opt in to the survey. And then in the survey, the user will provide a number of, essentially answer a number of questions and provide the answers to the survey questions. For example, including sensitive attributes of the user. And assuming that Meta then have this information, that the Meta, for a given user, Meta knows the user's sensitive attribute values and also knows the model inference results for the user, then Meta could compute the fairness results. And the fairness result there are different ways, different metrics that one can evaluate the fairness. As a simple example here, one can compare the average inference results for users identified as male, female, and binary as an example. So then in this case, as you can see, so if we have these different attributes listed as a Boolean vector, then essentially the computation, the fairness computation here involves computing, for example, the dot products of the user sensitive attribute vector and the model inference result. So this is how one could compute the AI model fairness. But however, of course, in this case, without more advanced cryptographic techniques, in order to do this, then Meta would need to know the sensitive attribute for the users. And of course, that is not acceptable. So instead, then what we want to achieve is a privacy-preserving AI model fairness measurement. So in this case, for privacy protection, Meta should now learn users' sensitive attributes, whether they are male, female, non-binary, and the survey operators can now learn users' inference results. And as everyone can see here, this is a great use case for crypto techniques such as MPC and so on. So this is exactly what we did. Together with Meta, we developed the cryptographic protocol and also built the system for this project. So in particular, in this case, the survey results will actually be secret shared across multiple facilitators. In this case, 3 universities, including historically Black university and also Hispanic university, joined as facilitators. And so the survey results are secret shared across the facilitators, and the model inference results in this case can be homomorphically encrypted, and then essentially we compute the dot products of the shared survey results and the encrypted inference results. And then in the end, so this will allow you to compute the encrypted result of this fairness computation. And also, and in addition, we also add differential privacy into the computation. And also, in this case, Meta also provides zero knowledge range proof, proving that the inference results that was encrypted was within a certain valid range. So this is the approach for doing this privacy-preserving AI model fairness measurement. As you can see, it actually uses multiple different types of technologies to put them together. But however, still, in this case, actually, putting aside the algorithm design, the protocol implementation itself, just the baseline, actually did not actually take a lot of time. So essentially, it was implemented within 1 month, actually a few engineering, altogether engineering month. But however, it took much longer. It took at least actually 4 or 5 times, or actually a lot more time and effort to actually build out a system so that the system can actually be deployed in real production. So if you look at for 3 engineers time, then like the initial base protocol development only took, as mentioned, less than 1 month, but the actual system, the production system development took actually many months to actually do it. So the lesson learned here is that there's a huge gap between the crypto protocol design and base implementation that can run on a single machine versus the actual development and deployment of a multi-party system that can actually run in production. And I would say most papers, of course, only focus on the very beginning of this phase of the whole journey. So that's the first example. And now let me give you the second example. The second example is another cryptographic protocol system that we have developed on privacy-preserving query processing multiple data sources. So the idea is to enable privacy-preserving SQL queries that can support rich SQL query primitives over data that's spread across multiple entities. So here's an example why one may want to do this. So for example, for credit assessment and fraud detection, oftentimes multiple banks need to together check whether a certain user who is applying for new credits, whether they have been borrowing from different banks. And hence, it's important to query across different banks for a given user, for example, to know the total balance for this user or the total balance for their credit cards and so on. So in this case, you would issue a SQL query, but the SQL query will need to be issued across multiple banks database. And then in the end, you want to sum the results. So then in this case, ideally, what you would like to do is you want a client to run the query without accessing the original records of the different banks, and but able to aggregate the results but can aggregate the results from the banks together in the end. And you don't want the client to know each separate result from each bank either. And also for the bank in this case, you actually may not want the bank to know, for example, which client is being checked, which user is being, which account is being checked. And hence, you want the bank to be able to process a query without, first of all, accessing the original records from each other, and also without knowing the specific query parameters that reflects the client's interest in the query. And also, you don't want the bank to actually know the final query results. And similar technique can also be used in a broad range of other application domains as well. So for example, in collaborative medical research, you want to essentially, for example, to query across different databases at different hospitals to check for results of a certain cure and so on. And another use case is in cyber threat intelligence, where one may want to query different companies and so on to learn whether a particular attack vector has happened or is a suspicious behavior has happened at multiple places. So all this together essentially requires the support of private query processing, where in this case, we have a client and a data provider, where the data provider could be coming from multiple sources. And the client wants to query these data providers for very rich, for example, data analytics and SQL queries that includes data retrieval, aggregation, different query types. And the clients should not know the original records of the data providers, and also the data provider in this case should actually now know sensitive predicates, parameters in the query. And this is different from, for example, peer due to the additional capabilities provided. So in our work, PrivShare, we developed the first fully homomorphic encryption-based privacy-preserving query processing over multiple data sources, where we convert the query using fully homomorphic encryption, and also have a query optimizer that optimizes the generated computation graph, the computation plan, and to enable more efficient results. And in our experiment result, we showed that we can actually make this practical. So for example, on the 32 core hosts, for simple aggregation query with the one equality check, we can process more than 1 million records within a minute, showing that this approach can actually be made practical. So again, here we ran into similar issues, as I mentioned earlier, with the Meta Instagram use case, where the original protocol design and implementation took a reasonable amount of time, like a few months. But however, to actually deploy the actual system actually takes much, much longer, a lot more resource to actually build it, to deploy it in production, in practice. So here from these two examples, we can see a common theme actually that runs across all the thousands of papers that I mentioned before. Also, all those papers are sitting on the shelf because there's a huge gap between the original protocol design and the single machine implementation versus actually having the protocol run in this decentralized manner and run in the real world. So making these cryptographic protocols real world deployable is non-trivial for protocol developers. And why is this? So there are many challenges besides the original algorithm design and creating proofs for security and so on. There are actually many real world system challenges when we try to deploy these cryptographic protocols in the real world. So for example, when we design the baseline implementation that just runs on a single machine, you don't really need to care, a lot of things you don't need to care about. But when you actually want to run the protocol in the real world, in this multi-party setting, each party will be run on their own machine, in their own system, and hence we need to handle, for example, a user's system and authentication, and also we need to handle a real-world communication and interface design between these different machines. And also, when you actually have these have the protocol running on these different machines, they need to have their own separate storage. That's each entity alone can only access its own storage. And also, when we have these systems running, oftentimes we need them to be able to run asynchronously. So, for example, with the AI model fairness measurements launch, our goal is actually to be able to evaluate over 1 million users. And for scale this large, we need the system actually to be able to run in a synchronous fashion and in a scalable fashion. And also in the real world, some parties may want to join a certain computation task, and some may not, or some may go online, but offline in other times. So there's a lot of negotiation among the different parties that's needed. And also for real world protocol deployments, we need to be able to have auditability, monitoring, and debugging, and so on. And there are many other challenges. And also in even more sophisticated settings, we can have even more challenges. So for example, in federated learning, we need to, there can be thousands of participants, and each has its own data and so on. So we need to be able to do even larger scale participant and data discovery. And also for more complex protocol, today it's hard to reuse existing efforts for like existing implemented protocols. How can we actually better leverage existing efforts when we build more complex protocols? And also in certain cases, we may need to handle heterogeneous computation resource as well. So again, this is a set of shared challenges that's not unique to just the two examples that I mentioned. It's actually unique. It's actually a set of shared challenges for any real-world applications of decentralized data collaboration and decentralized data science. So these are challenges for protocol developers. So hopefully we can help protocol developers to provide them better tools to address these issues so that we don't have these thousands of papers sitting on the shelf. Furthermore, when we look at actual application developers who want to benefit from all these developed protocol, crypto protocols, there are also many, many challenges today for them. So today, most of the crypto frameworks and systems are siloed, each with its own separate, either they don't even have a system for deployment, but if they do, oftentimes each has their separate deployment and system that's not composable. So essentially for a developer who is application developer who is building an application that may want to use different cryptographic protocols or different further learning frameworks and so on. Today, it's simply not possible for them to actually do this in an easy way. So for example, even just further learning frameworks alone, there are dozens of these siloed further learning frameworks. Each one has its own set of requirements and process for deployment and so on. And it's today, you simply cannot, application developers simply cannot easily use them together. And actually, even for them to try each one out takes them a lot of time and effort. And that's why even for these a lot of these developed frameworks, they are actually not really being used widely. So today, what I want to talk about is to address these issues, we are developing a new approach. In particular, we have been developing a new open source platform called CoLearn with the goal to make decentralized data science easy. So the goal for CoLearn is to bridge this gap that I just mentioned between the crypto protocol design and the real world deployments, so that we can actually make crypto protocol deployments orders of magnitude cheaper and faster. And also, we want to make it easy for application developers to utilize these crypto protocols as building blocks in their application. In particular, we want to be able to make all these different cryptographic protocols composable in a unified framework. And in order to achieve these goals, CoLearn has designed and developed a preset of carefully designed and standardized decentralized computing abstractions. And also it takes advantage of the recent developments in cryptography and privacy-preserving technologies. So with the CoLearn, the goal is to accelerate the research, development, and deployments of decentralized data science. So as I mentioned, for researcher and protocol designer, with CoLearn, it can help the protocol designer to reach real-world deployments much faster, much cheaper, and much easier, and hence help the protocol designer to lead to much greater real-world impact. And also by bringing the different cryptographic protocols all on the same platform, it enables standardized evaluation across different protocols and frameworks, and make it easier for comparison. And for application developer, CoLearn helps application developer to utilize cryptographic protocol building blocks much more easily and enable them to compose different protocols. And in this way, it allows application developers to benefit much more from the general ecosystem of new cryptographic protocol development, and also helps the application developer to be much faster to go to market when they want to take a responsible data use approach. And for the overall community, it also helps with better reproducibility, better protocol reusability, and help the whole community to come together to build a more vibrant ecosystem where we can really leverage each other's contribution to build something much greater. So with this platform and with its capabilities, CoLearn brings benefits of decentralized data science to everyone and to the whole society. For individuals, using CoLearn, it helps users to better maintain control over their personal data and provide stronger privacy and security guarantees, and help users to gain more benefits and fair value from their personal data. And for company and organizations, this helps the companies and organizations to break data silos to make it easier for different companies, organizations, and also for even within the company for different departments to make it easier for them to collaborate across boundaries, to cross data boundaries, and reduce the negotiation efforts, and with better data use, help the companies and organizations to lead to better products and services. So far I've talked about the vision and the goals of CoLearn and the benefits of CoLearn. So now let me briefly talk a little bit about the internal of CoLearn, what actually made it possible for CoLearn to achieve this set of ambitious goals. So as I mentioned, what makes CoLearn unique and uniquely capable for this is that CoLearn has a preset of carefully designed abstractions, and in particular, these abstractions are first of its kind and particularly designed for decentralized computing. And in particular, as I mentioned, when we need to deal with decentralized computing, instead of in Web 2.0, where you simply have a centralized trusted third party to handle the computation, one needs to handle a lot more different actually challenges when it comes to decentralized computing. And to make decentralized computing easier to do, we need new abstractions for this decentralized computing. So this includes decentralized user identity, and here decentralized data use registry, and we developed a number of different decentralized programming abstractions, and also decentralized protocol encapsulation, so that we can encapsulate decentralized protocols as building blocks to make it easier for other developers to use. And also for deployments, we make it really easy for deploying protocols and applications running on CoLearn. So essentially with the one-click deployments in both cloud and on-prem settings. So now let me briefly go into these abstractions just at a very high level, given interest of time. So first, for user identity, again, here we embrace Web 3.0. So with the Web 2.0, essentially users do not even have control of their own identity. Users relies on essentially the identity providers to help them with authentication based on oftentimes, for example, their username and password. So in CoLearn, users have their own user-owned and user-controlled identity. So each user has their own public-private key pair so that they can control and own their own identity. And this enables CoLearn to seamlessly integrate with Web3, other Web3 applications as well. And with the user-owned identity, this also makes it easy to verify users' identity across different services, again, without relying on any central trust. So users can use user-controlled identity to verify across, for example, storage, communication, other decentralized tasks. Right, and also this end-to-end verification can help trace the whole chain of trust. And so CoLearn provides open source SDK to make many tasks on decentralized user identity easy, and a user can use existing tools such as connecting with MetaMask to log in, which is the most common login tools in Web3 and cryptocurrency today. And with this decentralized data science, we need to have a public data registry to actually help us to understand which users are participating and what data they may want to use to join collaborative this decentralized data science tasks. So again, here CoLearn does not rely on any centralized trust. So the data registry can be provided on the distributed ledger. The data content itself never leaves either user's own private storage or can be stored in encrypted form in decentralized storage. And the user gets to define policies for its own data, how its data should be used. So essentially provide fine-grained control for users over the usage of their data. And CoLearn also provides a framework to help with the standardization of data format and the metadata format and so on. And with the public data registry, it makes decentralized data science much easier. As a data consumer, for example, a medical researcher or others, there are some other applications. And they can then search through the public data registry for proper data sets with matching usage specifications. And also they could even purchase certain tokens or authorization code to be able to use the data, certain data in a policy compliant way. CoLearn also provides a number of novel decentralized programming abstractions. So let's look at the difference between traditional programming abstractions in the traditional setting when the process is run on a single machine versus abstractions for decentralized programming. So in the traditional setting, a process is run on a single machine, and in general, you don't need the concept of user, and the process essentially gets to have access to its relevant data, and the communication is handled as I/O. And also in this traditional setting, essentially you have libraries with functions that can be used. So when an application developer that wants to, for example, leverage or reuse existing functions, they can just include a library and then call the function that it needs. But however, when we look at decentralized computing, things are very different. So in this case, a given protocol, as I've shown in the earlier examples, its execution will actually run across multiple machines. And also it involves multiple users, so it needs to have a notion of the different users. And each machine, each node may have access to its own private storage and may have different views of data available, and also need to be able to handle communications across different machines. And in particular, in this case, if an application developer wants to reuse a protocol that actually runs across multiple machines, it cannot just simply include the protocol as a library and then just call a function in that library. Because in the traditional the traditional setting, that simply you simply cannot do this in the traditional setting or with the traditional approach. So in CoLearn, we provide new programming abstractions to enable these type of decentralized computing to help address all of these challenges to make it much easier for protocol developers and application developers. So in particular, in order to be able to reuse these cryptographic protocols that actually run across multiple machines, multiple parties, as I mentioned, the traditional notion of a library simply is not sufficient, simply cannot actually do the job. So in CoLearn, we developed a new mechanism to encapsulate these multi-party protocols that run across multiple machines. And so essentially we can encapsulate these multi-party protocol implementations as extensions. And also we can encapsulate them as extensions and enable ease of use of this encapsulated multi-party protocols. And we also provide a registry for these multi-party protocols in a protocol registry that also can be stored on a distributed ledger so that it doesn't, again, doesn't require any centralized trust. And CoLearn also provides automatic execution environment management as well. And CoLearn provides built-in mechanisms to enable easy deployment of CoLearn system in both cloud and on-prem environments. So for cloud deployments, we can enable one-click deployment across multiple clouds with auto-scaling using underlying tools, SkyPilot. And also CoLearn provides capabilities for automatic service discovery and credential management with the data use registry, and also automatic version and dependency checking with the protocol registry. So to put all these together, CoLearn, here's the CoLearn architecture. We won't actually go into the detail for the different components within a CoLearn server, which actually handles all these, provides the abstraction of communication, storage, user management, and task scheduling, and many other capabilities. And on top of the CoLearn architecture, we essentially provide two different types of SDKs. So one type of SDK is for protocol designer SDK to enable researchers and cryptographic designers to build their build their new protocols. And then once they implement their protocols on CoLearn, essentially CoLearn can handle all the rest of the system development and deployment, as I mentioned earlier. And also in addition, CoLearn provides application developer SDK, which enables application developers to more easily use existing cryptographic protocols as building blocks inside their application. So with the CoLearn architecture and platform, as I mentioned before, so with the protocol designer SDK and the application developer SDK, this helps the protocol designer to get their protocol from design to actual real world deployment much faster, orders of magnitude faster and cheaper and easier, and also make these protocols much more easily used by application developers. So to summarize, I mentioned previously a list of many challenges for bringing cryptographic protocols to real-world deployment. And with CoLearn, with the abstractions that I mentioned, including decentralized identity, the decentralized programming abstractions, decentralized protocol encapsulation, the data use registry, and also one command deployment, and many others, this can address the many challenges that I mentioned and significantly simplify decentralized data science. So with this, CoLearn reduces the time and effort from design to deployment for new protocols by orders of magnitude. So as I mentioned, in the first example that I mentioned, the privacy-preserving AI model fairness measurement, with the CoLearn platform, it can reduce the actual system development deployments from many months to just a couple weeks. And similarly, for the second example that I mentioned, for PrivShare, for privacy-preserving data analytics, similarly, it can significantly reduce the system development and deployment from many months to a few weeks. And the CoLearn's application usage scenario is far broader than the examples that I have just mentioned. So another example here is also our recent work in collaboration with researchers at Berkeley on developing new approaches for proactive dynamic secret management, proactive dynamic secret sharing. And then in this particular case, we can actually reduce the system development and deployment effort from many months to actually just a few days. So CoLearn doesn't just make developing new crypto protocols easier. CoLearn can also easily integrate existing protocols and frameworks into this unified platform for composability and ease of deployment. So for example, in CoLearn, we have integrated with leading privacy-preserving machine learning protocols and frameworks, for example, in this case, Krypton, to make it much easier to deploy Krypton, and also at the same time to enable composability to make it easier for application developers to use Krypton and in addition to other crypto protocols. And another example of integration is CoLearn also has integrated state-of-the-art federated learning for including both horizontal and vertical federated learning into the platform, including Flower for horizontal federated learning and FedTree for both horizontal and vertical federated learning as examples. And also we have ongoing work on using the system to build a federated learning framework benchmark so that we can more easily benchmark across the dozens of different federated learning frameworks and help developer to best choose which federated learning framework is the best for their use given their particular usage scenario. So, all these are examples that CoLearn can make it both easier for crypto protocol developers to build new protocols, as well as integrating existing protocols into the platform for better composability and ease of deployment. And CoLearn provides a unified platform today with the state-of-the-art cryptographic protocols, including these examples that I mentioned, and some are still in progress for final integration. So with all these integrated cryptographic protocols, as I mentioned, CoLearn also makes it really easy for application developers to utilize these built-in cryptographic protocols. So here is just one example that we provide as an illustrative example. So in this case, we use CoLearn to build actually the first decentralized Texas Hold'em tournament in the real world. And so this poker game uses MPC protocol with the secure shuffling, and also provides cryptographic certificates of game results for score tracking. And we have easy integration, so users can actually just simply play using Telegram. So all this, so this is an example illustrating the ease of building decentralized data applications on CoLearn. And normally this would take, again, many months of work, whereas using CoLearn, it actually takes significantly less time, only weeks. So when we have a system like CoLearn, we can truly enable what we call decentralized data science and build what we call data commons for decentralized data science. So in the setting, users are data owners. They can register their data sets with their data use policy specified in this decentralized data catalogs. And data consumer and analysts can search through the data catalog to find relevant data. And they can write data analytics and machine learning programs over different data sets and data sources. And then the data analytics and machine learning program, essentially that's built on CoLearn, can then be run across the different entities, across the different machines in this secure distributed computing platform, while ensuring the program is compliant with the desired policies. With this approach, it can significantly reduce the friction of data usage and remove data silos and enforce security and privacy protection. And with decentralized data science, we can have broad spectrum of use cases to benefit society. So for example, one can use federated learning to gain data insights from multiple medical institutions to conduct collaborative medical research. And one can, and also we can use CoLearn and a platform to enable, to provide personal data vaults to allow individuals to use, to have their, to enable their data to be utilized without compromising privacy. And then in this case, even for the survey, so for example, in the AI model fairness measurements, there I mentioned there's actually a survey operator. And then in that particular case, the survey operator actually knows the survey results. But with decentralized data science and CoLearn, we can even run, and we can organize these vote and surveys without even requiring a centralized survey poster. And also, we plan to conduct decentralized large model training and integrate and enhance existing frameworks to further optimize the performance in decentralized setting. So with decentralized data science and data commons, I truly believe that this will become a commonplace in 10 years. So in 10 years, we'll have these data trusts and data commons to be the predominant ways for utilizing diverse sources of data, enabling ownership economy where users benefit from their data as owners and partners. And also in 10 years, we'll have data stewards, fiduciaries, and trustees, and to be a new class of entities important in the data ecosystem, managing, protecting users' data, and growing its value. So essentially, they can help users to adopt, set their data use policies that best help them to benefit from their data and provide privacy protection for their data. And in 10 years, huge economic value will be created through these new forms of data trust, data commons, orders of magnitude higher than today's data marketplace. So, so with that, I hope everyone got a glimpse of the visions, the goals, and the capabilities of CoLearn. So what I would like to encourage here is to encourage everyone to try out CoLearn and use CoLearn to build your own protocols and applications. So we are preparing for an initial release very soon, hopefully by end of the month. And with this release, it will include open source CoLearn server implementation and also the SDKs that I mentioned in multiple languages, including Rust, C++, Python, JavaScript, and so on. And also, it will come with the integrated protocol examples that I mentioned. So I hope that you can join us and start your journey on contributing crypto protocol building blocks and writing easy to use decentralized data science applications using CoLearn. Again, the whole community has developed such great algorithms and huge advancements in the technologies. So instead of just having the thousands of papers sitting on the shelf, the goal of CoLearn is to make it much, much easier and essentially bring orders of magnitude improvements to make it easier to bring these cryptographic algorithms and these thousands of papers into the real world. So with that, to stay tuned, you can join us on the mailing list at this Google group, CoLearn-Dev. Thank you.
Thanks a lot, Dawn. So let's have some questions. Yeah, do you want to come here?
Hi, Professor Damson. I think this is quite an interesting talk because we have a lot of analogies we call blockchain decentralized AI. And today I heard something you developed CoLearn is decentralized data science. So I'm wondering what is the connection? So for example, right now, for behavioral science, we use O-Tree. It's like a centralized platform and also Amazon mechanic term to collect the user's data. It sounds, it cannot protect the user's privacy. Also, there might be a lot of bots pretend to be the subjects to answer a service. So it sounds like your plan for can help us solve those problems. So I'm just wondering whether what's the connection between we deploy the software on blockchain and we deploy the software on your platform. Thank you so much.
I see. Okay, great. Yeah, thanks for the question. So, as you can see, so CoLearn also leverages blockchain distributed ledger for its registries, so it doesn't need to rely on any centralized parties. So, however, for the kind of application that you mentioned, you actually can't, you cannot just do it using blockchain. Like today's blockchain, all the data and compute on the blockchain is all public. So for sensitive data, you cannot really put on the blockchain, and you cannot do this computation on sensitive data on the blockchain either. So that's why. So with CoLearn, it's a carefully designed and that utilizes different essentially cryptographic protocols for secure computing, and you can, and then you can use blockchain for certain right coordination, registry, and so on. And also, right, so Colin will continue to integrate other capabilities as well, including secure computing in a secure enclave and right, and other capabilities. And also, right, I'm happy to discuss offline as well to learn more about your application and see how we can help.
Oh, hi. I was wondering about in the first part of the talk where you described some protocols that use FHE. Could you clarify who generates the key pair for the FHE and how that?
In that case, the client who makes the query.
But aren't there multiple clients?
And that's a very good question. No, here, like I did, right, let me just clarify the notion of the clients. So we call the client is the one who actually, who wants to query, who actually needs to get the query results. And so that's the client. And then you have multiple servers, like the data providers. So, right, so in this case, right, the clients.
Wait, so are there multiple clients and that client, those clients trust the client that generates the keys? Is that what goes on?
What do you mean by multiple clients? In certain use cases, you may have like different clients to do different queries. Then in that case, right, they can do their own right, do their own encryption.
Yeah, I think I was just confused. I thought there was multiple clients.
So you only have multiple data providers, and those are now called clients. And you only have one client who wants to make queries across these different data providers.
I see.
And then over time, of course, you can have different clients, but each one then will be doing a different query, and then they can do their own encryption.
Okay, I see. Thanks.
Mm-hmm.
Hi, thank you for the talk. I have several questions about PrivShare as well. Have you considered joining different data sources from the different data providers as well when you were working on the project?
Yes, it's a work in progress.
Okay, it's just a few more follow-up. By query optimization in PrivShare, what do you exactly mean by that?
Oh, so essentially, when you create this computation plan, and there are optimizations you can do to reorder certain operators and so on, so that you can better utilize FHE's right, the capabilities to reduce performance overhead.
Okay. The last question is: are the aggregates enough for the privacy protection? You're providing some count, average, and then minimum and maximum. Is that, well, just providing the fully homomorphic encryption over the computation circuit, is that the query results itself, it seems, after the decryption is not really protected for the privacy. What's your take on that?
Oh, so in this case, the client wants to get the query results. So the clients, right, as I showed in the examples, the client wants to right, conduct a particular, let's say, SQL query, and then the client wants to know the result. That's the problem definition. And then in the future, of course, if you want to add additional like DP noise and so on, and that's an additional thing that you can consider. But right now, the problem definition is such that the client has a SQL query it wants to run, and it wants to get the result from that.
Okay, so you're assuming that the client is not malicious.
The client, in this case, needs to know the result. That's the client's goal. And that's a problem definition. And right.
All right, thank you.
Mm-hmm.
Are there more questions? I have a quick one, Don. So how really easy it is to integrate existing protocols? Let's say we have an MPC library already. So how easy it is to integrate GoLearn?
Okay, yes. We'd love to discuss the right, more details after this too. So actually for the integration, there are different levels of integration. We call it the lightweight integration, are deeper integration. So depending on the integration level you want to do, so for example, like for Krypton and so on, actually didn't take very long. But right, of course, it depends on the details, but we would love to discuss more details with you, and we love to integrate some of the protocols that you guys have already developed into CoLearn as well. So as an example, like this is the dynamic, the proactive dynamic secret sharing. So that one actually would, like I said, so that one actually is really simple. It's only like a few weeks, a few days, or like a week or something at most. But right, so it also depends on like what you have currently. But we would love to discuss in more detail. And it'll be great to integrate your protocols into CoLearn.
Right, looking forward to see your documents and collaboration.
Right, great.
Thank you so much. It's kind of unfortunate we don't have you in person, but we will see you soon. So thank you so much.
Great, right. Thank you.